Hello, welcome to Pipeline Integrity Gamma Exponent Model Validation Part 3. My name is Colin Scott. I'm a pipeline integrity engineer based out of Calgary, Alberta, up in Canada. Today's topic is going to be gamma exponent model validation for corrosion and metal loss flaws. Some of you that have seen my other pipeline integrity series may have seen this already, but we're going to build on things and add a few statistics that you might not have seen before. Now, the gamma exponent model for localized metal loss is a very, very simplistic looking model. We have our predicted failure strength divided by our flow strength, and that's equal to the remaining ligament to the power of the gamma exponent. In the case of localized metal loss, the gamma exponent is the minimum of the length of the corrosion flaw divided by the radius of the pipe. And that goes up to a maximum of 1/2. Now, this looks like a very simplistic model that many of you may think was just sort of empirically pulled out of thin air and it seemed to work. That's not actually the case. There is a mathematical and theoretical rationale behind it. And in particular, there is a theoretical and mathematical rationale behind that gamma limit of 1/2. In order to understand that, though, you'll have to dig through my ASME Journal of Pressure Vessel Technology paper that I'll show you a little bit later on. For now, we'll just keep things simple, though. Now, the fine print on this model is that I can modify it by a pi/4 to approximate a semi-elliptical profile. So this is a fairly common thing that's done in our business to try and account for profiles when we're not entirely sure what they look like. If we do have a full profile available, then I've developed a level 2 algorithm, which I call the ELM, and that can be used for a more refined prediction. At this point, I'm not going to tell you exactly how that ELM algorithm works. I'm trying to get that published in a real place, and so I need to keep a few secrets for them. I will show you the results of that algorithm, and it seems to be, at this point, quite effective. The flow strength I've used for validation was the yield strength plus the 69 megapascals or 10 KSI if you're south of the border. I have not messed around with the various other ways to define the flow strength. The derivation of the GEM model is essentially a flat plate solution, so I really limit everything to thin-walled pipe, and I've come up with an arbitrary limit of d over t has to be greater than 20. And as I mentioned earlier, the gamma exponent limit for metal loss is 1/2. Now, that limit of 1/2 is going to cause some of you an enormous amount of concern because it means that the remaining strength for a corrosion flaw, as that corrosion flaw gets longer, is actually equal to the square root of the remaining ligament. And that's a very unusual thing. Before getting too worried about that, though, I would like to suggest that you look over my ASME journal article, or you can look over one of my previous videos, Pipeline Integrity, Things That Make Me Go, video number 2. And that will demonstrate that mathematically that square root relationship is actually legitimate, although I know a lot of you will be skeptical. As far as industry failure data goes, I've got two very good sets. One I'll call the Cronin data, and that's from a doctoral thesis from the University of Waterloo in 2000. Now, there are 40 complete data sets, and of those 40 data sets, there are actually 23 full corrosion flaw profiles. So that allows me to demonstrate not only the simple form of the GEM equation, but also my level 2 ELM algorithm, and I can demonstrate to you how much of an effect that level 2 algorithm has on failure pressure predictions. Now, anybody that's in the business that wants to play around with numbers, the Cronin data is easy to find online. If you just do a Google search on Dwayne Cronin, Waterloo University, you'll be able to find it fairly easily. I also have a second set, which I call the Patel data, and this is from the Pipeline Research Committee of the American Gas Association, way back in 1974. And this includes 45 data sets. And these data sets would have been used by the NG18 committee of the Patel Institute back in Columbus, Ohio, to actually validate the original B31G type equations. So this one is a very, very valuable data set. It's not quite so easy to find those, so you might have some trouble there. Now here I've got a simple validation plot where I've said on the y-axis I have the predicted failure strength, on the x-axis I have the true measured failure strength, and if I make the assumption that all of these metal loss features are approximately semi-elliptical, I find that the validation effort turns out fairly well. you'll see that I have some data points that are above the line, indicating that they are non-conservative and potential safety concerns for the pipeline. But I have an equally balanced number of data points below the line, and these are overly conservative. When I see how these all match up, I find that the trend line gives me a slope of y equals 0.92, meaning that on average, this model is about 8% overly conservative. And that's pretty good. If you were to look at, say, R-string, if you look at the corrosion data, or if you look at recent PRCI efforts, you'll find that the R-string algorithm is actually about 30% overly conservative. So this is really a step in the right direction. The most refined model that I'm aware of for corrosion and metal loss is the p-squared model that was put together by the Trans-Canada Research Group working with PRCI. And they managed to improve their algorithm to about 13% overly conservative, which is pretty good. Now, if you look at my accuracy with this semi-elliptical assumption, my accuracy I think is a little bit better than the p-squared model currently is, but at this point I don't have particularly good precision. There seems to be quite a bit of scatter in my data points, and that's where a model like p-squared is much more precise. You would find that with p-squared, those data points would be quite a bit tighter. Now, what I have done is I've come up with my own level 2 algorithm. I call it the ELM. I'm not going to share it with you right now. I'm trying to have that published through a real publication. But what I found is that when I use it on the 23 full profiles from the corrosion data, I find a big improvement. Here I have a trend line that goes through my data points of y equals 0.98, which means that that's about 2% overly conservative. But you've seen that the data points really tighten up. And we'll look at some statistics later on that show you that the precision I've got here is actually comparable to what p-squared has. Yet I seem to have pretty good accuracy compared to p-squared. So the mathematical efforts that I put into developing the model seem to be improving predictions pretty well compared to some industry available models. If I take a look at some very simple statistics, I can look at the basic GEM, the basic gamma exponent model, and assume a semi-elliptical flaw shape. Now, if I take the failure ratios of all those data points, and I take the mean of them, I will find an accuracy estimated at 1.09. So there we're about 9% overly conservative. When I mention the failure ratio, I mean the ratio of the true failure strength divided by the predicted failure strength. If I look at the precision of those data points, I'm really just looking at the standard deviation of the failure ratios, and I come to the number of 18%. So that's pretty good. And I think that you'll find that that accuracy is improved over R-string and p-squared, but with the basic GEM, it does not have the precision of an R-string or a p-squared. But then if I move to the level 2 ELM algorithm and look at the full profile, I'm able to get an accuracy that's improved to 1.01 and a precision of 8%. So with those numbers, I'm making things a lot closer to reality. I think that mathematically speaking, this is a step in the right direction in terms of failure pressure predictions, and this potentially can save an enormous amount of cost for some of the larger pipeline operators that spend gazillions of dollars on digging up corrosion flaws that they don't necessarily need to. If you're interested in further viewing, I'd like to point you towards my earlier series. It's called Pipeline Integrity, Things That Make Me Go, and that's a 6-part video series. In that case, it's a critique of the NG18 based assessments for both corrosion and cracking. When you look at the NG18 equations, they mathematically focus on flaw length, and they really shouldn't be doing that. When it comes to surface cracks and surface corrosion, depth is a much more important parameter, and a lot of the development in my GEM equation has been in flipping everything from a length-based model to a depth-based model. If you look at some of those videos, they're about 10 or 15 minutes each. You'll get a better understanding of how I developed the model and why I developed that model. If you've enjoyed this this video, I'd also like to suggest taking a look at the other parts in this video where I look at some other flaw types, including axial and circumferential surface cracks. I look at axial stress corrosion cracks and then through wall cracks for leak rupture boundary analysis. So please dig around on YouTube and you can find those fairly easily. If you're more interested in reading than you are in viewing, I do have some real papers that have been published. Please feel free to dig those up. If you're mathematically minded and are curious where that gamma exponent of 1/2 limit comes from, I'll point you towards the ASME journal Pressure Vessel Technology, where I go through the rigorous mathematics of derivation of the model. Although this model you're seeing seems to be fairly simple and empirical, there's actually some technical rationale and mathematics behind it that's quite important. If you've made it this far, thank you very much for your time and attention. I hope I've given you some things to think about. As I said, please dig around on YouTube and find some of the other validation videos if you're interested. And I'm hoping to take these failure pressure predictions in the right direction for the industry and hopefully save a lot of unnecessary repair costs for the various operators. Until next time, thank you very much for your time. Have a good day.